Now we have the rest of the cases of L'Hopital's rule. We already saw the 0 over 0 case, and also x going to a real number. But it turns out that you can also use L'Hopital's rule in the case of going to infinity, plus or minus or plus. And this x can go to infinity or negative infinity, and you will still be able to apply this L'Hopital's rule, where we sort of in a slang way here said that x could be going to infinity or negative infinity or any real number. And as long as you have these cases of 0 over 0 or plus or minus infinity over plus or minus or plus infinity, then everything's going to work out and you can apply L'Hopital's rule. Here's an example. We have this example here, and it's not really obvious what's going to happen as w goes to negative infinity right here. So we'll just check the case to see if we can employ L'Hopital's rule. So as w goes to negative infinity, we substitute in for w here and here, and we see that the numerator indeed goes to 6 times infinity, and e to that is definitely infinity. And the denominator, if you put negative infinity in for w, 3 times infinity, and e to that is certainly infinity. So it's an infinity over infinity case. Alright, so now we go on to evaluating the limit. We take the derivative of the numerator, and here it is. Derivative of the denominator, and here that is. And then we do a little bit of algebra. 6 divided by 3 is your 2. And e to the negative 6w divided by e to the negative 3w is e to the negative 6w plus 3w, which is negative 3w. And as x goes to negative infinity, negative 3 times a real large negative number would itself be very large positive, so that it goes to infinity. And of course, all of these problems you can always check with your TI. I set up a table. I put the function, the original function, into y1, and in this case I want to go to negative infinity, so I want to have a delta table that's negative 1 going down, proceeding lower and lower to the left on the number line. And you can see that the numbers get bigger and bigger and bigger until finally this one right here, for example, 3.27 E6, that means 3.27 times 10 to the 6th, that's 3.27 million, so we're definitely going to infinity. And we have another example here. Limit of x log x. But that doesn't seem like a L'Hopital's problem because we don't have a quotient. We have to have a quotient. Well, we can just rewrite this x here as 1 over x. So we just rewrite it like that. Now we do have a quotient. And let's check to see if we have one of the proper forms. As x goes to 0 from the plus side, log x definitely goes down to negative infinity. And of course we're going to 0 from the plus side because we can't come from the negative side or even equal to 0 because the log would not be defined there. The denominator, as x goes to 0, that definitely goes to plus infinity because you're coming from the right side of 0. So it's a negative infinity over infinity case, which is fine. So we take the limit, we take the derivative of the numerators, 1 over x, derivative of the denominator, negative 1 over x squared. Then algebra cancels out and you get negative x. And when you go to 0, you'll have negative numbers, but they will limit out to 0. And I provided a TI. I set the table to ask for the x value. I'm going to 1. I'm going down towards 0 from the right and my y values do indeed look like they're getting smaller and smaller and smaller, headed toward 0. Here's another example. Which rises more slowly as x goes to infinity? Square root of x or log x? So you could also ask that with which one rises more fast, or faster for the whole thing here. Having a little fun with my English here. So basically, if the limit as x goes to infinity of square root of x over log x, if that goes to infinity, then that means square root of x dominates and rises faster than log x does. If, on the other hand, if as x goes to infinity, square root of x divided by log x goes to 0, that would mean that log x dominates and therefore rises faster. So the question is, which curve is which here? Over here on this graph. Is the top one square root of x or is it log x? Let's find out. So in the original limit, as x goes to infinity, square root of x definitely goes to infinity. As x goes to infinity, log x definitely goes to infinity. So we have the infinity over infinity case, which we can use L'Hopital's rule. So we look at our limit and we take the derivative of the numerator, which is this, derivative of the denominator, which is this, do our algebra, come out with this, and as x goes to infinity, square root of x definitely goes to infinity, so that means that square root of x wins out and rises faster and faster than log x. So on our graph up here, this was square root of x rising faster, and this was log x. They both rise slow, but log x is a lot slower. And when you think about it, when you have a logarithmic, that really does knock down the size of the x argument drastically.